go and do some science. So today I'm going to talk about get you going on the path to performing power analysis. And power analysis, the idea is that previously the attacker had one kind of input, which is the timing, and this got us a bit far, quite far, but you can do constant time countermeasures. And now we're going to talk about another kind of piece of information that the attacker can have, and this is the power consumption. So I'm going to talk about why devices consume power, how they consume power, and how do you measure it. And this will take us through today. And next week, the week after the next, God willing, we will do some attacks using this, what is called simple power analysis. It's called simple, not because it's simple, because there is something else which is a little less simple. So we'll get a touch of that. And after that, Stefan Pichek will give us an incredible demonstration of what you can do with power analysis. So let us begin. So who here took some kind of course in circuits or university level physics, פיזיקה 5 יחידות? Okay. So I see I have like a mixed audience here. Some people know electrical engineering, some people not. No, you see, everyone I guess is why you need to teach this course several times. And it's very important when I only see myself to understand what people know and don't know. So we're going to learn digital design and electronics basics in a very innovative and new way, which I just thought about last week. We're going to imagine we're electrons. We're going to have a mind experiment, and let's see how it works out. It could be either fun or I don't care. So what I want you to remember while I'm going through this introduction is that this is an attack course, and I'm not teaching you this for any other purpose other than attack. So everything I teach you, I'm teaching you so the attacker can think, how can I do something offensive using this? How can I recover a secret using this? So let's start with the very basic. First of all, I want to say that if you want to learn about digital power consumption and so on in more detail, I'm going to be referring a lot to this book. This book, the power analysis book, is wonderful, and it has a lot of theory and definitions and serious explanations of what I'm going to be hand-waving my way through here. And what is nice is that even though you're all at home, you don't need a VPN to get to this resource. What you do is you click on this link, the BGU library, and then you search for power analysis attacks. You search for it, and then you do view online, and you just get the entire PDF, and you don't need a VPN. You just put in your BGU password. You get the entire PDF. So there's no point of getting it illegally because it's so easy to get it legally. So please support your local library and get it from there. So I'm going to be skimming over a lot of things which are described here in more detail. If you're curious, it's very, very well written, and it's got also some summaries. So if you want to skip and you only read the boxes with the important stuff, it's also designed. So it's designed for an engineer. So now let's look at the most basic electronic circuit that I can think about, and this is so who here is seeing electronic circuit for the first time? Who has never seen this figure before? Never seen a basic electronic circuit. Okay. So fantastic, right? So you see, some people have never seen this before. So let's see what we see here. This is a very basic electronic circuit. What we have here is the VDD. This is a power supply. It could be a battery, USB port, could be the power port, and so on. And there is the ground. The ground is where the electricity wants to go. The electric potential wants to go, and there is a flow of electrons. This is the current. They are flowing, and they're going through the load. And the load is the piece of the circuit that does the actual work. Uh, Various things you can do with electricity, and we'll talk about it a bit later. But this is the basic electronic circuit. And so some people who have learned electronics, it's very intuitive and trivial to understand what's going on with electronics. But the problem is that electronics are what Bibi says, it's the invisible enemy, right? We can't see it. Uh, so it's a little hard to imagine what's going on. So fortunately, there's a very nice metaphor for electronic circuits, and that is water. So you can imagine that the power supply is a spring of water somewhere in the mountains, and then the ground is the sea. And the water, it wants to go down to the sea. So the water always wants to go down, and obviously the water will choose the easiest way to go down. And if there's a steep decline, it will go quickly. And if there's a lot of bushes and sand and stuff, it will go slowly. And so you can imagine that the potential is the altitude and so on. And another way of imagining this, also involving liquids, is that we are now at home in London University. And one of the things, what do we miss about campus? What is the thing that we really, really miss? Going out on the break and getting some what? What do we miss? What do we buy on the breaks? We would buy freedom. Yeah. So we would buy, of course, we want to buy some excuse me, we want to buy some what we want to buy is, of course, hold on, some ice cafe, right? This is what we really like to buy. So if you don't know what ice cafe is, it's a drink which is very thick. And to drink our ice cafe, we have a straw. So now we imagine that we bought a cup of ice cafe and we have a straw. And obviously, since we had Corona, we have a very weak respiratory system. So we can give a very, very weak schluck. We're not very powerful right now. We're still recovering. So we're drinking the ice cafe from the cup using the straw, and we're getting a certain amount of ice cafe per time unit. So the current is the ice cafe coming out of the cup, and we can measure how many units of volume you get per time, and this is the current. So now let's assume I've just had Corona. I'm really having a terrible time drinking this ice cafe. So I get another straw, and now I have two straws. And what I'm going to do, I'm going to take this new straw, and I'm going to put it next to this straw which I have, and I'm going to drink out of the two of them together. Now, and I'm going to give the same power, the same schluck power that I had previously. So what is going to happen to the amount of ice cafe that I'm getting using these two straws? Will I be getting less ice cafe, the same amount of ice cafe, or more ice cafe? If I have two straws now in the cup of ice cafe. So per unit of time, yes, per unit of time. So yes, I agree with you. If I have two straws and they're both resisting, the ice cafe, but they have two of them. So now I'm getting twice as much as ice cafe per unit of time. Okay, fine. And now I have another idea. What if I do the following? I take the new straw and I put it inside. I connect it to the old straw. Now I have a really, really long straw, and I'm trying to draw the ice cafe using this new contraption, this double-sized straw. So will I be getting less ice cafe, same amount, or more ice cafe using this contraption which I made? What are your opinions here? So actually, most of you think that you're going to get the same amount of ice cafe, and I don't agree with you because I'm going to have to fight twice as much as resistance from, from the unit of time, from the friction inside the straw, and from the gravity of the ice cafe pulling it down. So I think that I'm going to be getting less ice cafe. And now the third question. So this is parallel and serial. Thank you, Oren. So if I put the two straws in parallel, I will be getting, after I stay at home a couple of days longer, I'll be a professor. Yes, thank you. If I have the ice cafe straws in parallel, I will get more current. If they have them in series, I will get less current. And now the third question, that is more challenging. I take the straw and I add in parallel to the straw a very, very thin straw, the thinnest straw you can imagine. It's going to be a piece of macaroni, okay? A very, very thin straw, and I'm going to be schlucking from the both of them, a really thin straw. So what is going to happen to my ice cafe supply? If I add a really, really thin straw in parallel to the existing straw. The infinitesimally straw. It's really like spaghettini, okay? Really, really small straw. So your insights are very interesting. So actually, what I'm going to get is essentially the same amount of ice cafe, because the resistance of this tiny straw, this piece of spaghetti, is so large. It resists the flow so much that basically I will only be getting my ice cafe through the regular straw. So now that we finished with the ice cafe metaphor, let's go back to the electrical circuit. So this, what you see here, is called Ohm's law. And Ohm's law connects the three values of voltage, current, and resistance. And what it basically says is V is equal to I times R, and where V is the voltage, and I is the input, and R is the resistance of the load. So, thank you. Thank you. So I'm claiming that the voltage is usually fixed. And why can I claim that? Because it's coming out of a power supply, right? A battery or a charger or the power. So it's basically fixed. So if I fix V, you see that I and R play. If I fix V, then I and R play with each other, right? If I lower R, I get more current. If I raise the R, I get less current. Fantastic. Now, please tell me. I have a phone here, and I want to make my phone's battery run out really, really quickly. What should I do with my phone? What things can I do to make the battery run out? Okay, I can turn on the screen, right? I can do some kind of computationally intensive thing. Yeah, I can all the bro chains here. Yeah, okay. What else can I do to make the battery run out really quickly? Okay, I can play games. Beat it. Oh, you can do it to your phone. Short circuit your. I can make a call, maybe. Maybe I can make a call, right? Turn on the flashlight, uh, and maybe make it play music at a very loud volume. So, and when I'm doing this, the battery is running out faster, right? What is stored inside the battery, by the way? What is stored inside the battery? What does it store? Voltage? What is inside the battery? When you buy a new phone, what you say this battery? It's what? It's 3,000 what? $3,000? 3,000 mAh, right? 3,000 milliampere. 3,000 kilogram. So it's not OL. I have to correct you. It's not milliampere divided by hour. It's milliampere multiplied by hour. So it's milliampere times hour. Okay. So milliampere hour means that if I have a 3,000 milliampere hour battery, it means that if I have, if I'm consuming 1 ampere of current, how long will my battery last until it runs out? 3 hours, right? So hopefully it will take less. But you see that my battery lasts more than 3 hours, and you can understand from that that sometimes the phone consumes a lot of current and sometimes less current. So what does that mean? The voltage is more or less constant, and the current is changing all the time. And that basically means that the resistance, the instantaneous resistance of the phone is changing all the time. And it's changing as a function of what I'm doing. If I'm making a call, doing a calculation, mining Bitcoin, and so on. And now as an attacker, you can kind of see the wheels turning here, right? If I'm an attacker, maybe I can look at the power consumption and learn what the user is doing. Okay. So another law which is useful for us is this function which maps power. This is how we calculate power. Now, power is an instantaneous measurement, just like current. So the battery doesn't have power, the battery has current. So it's work over time. It's a very momentary thing. And to calculate the power, you multiply I times V, and you measure this in watts. But you can also, you can assign, you can substitute, it's I squared times R, or V squared divided by R. Fine. So, what do we use power for? What things can I do with electricity? What kind of work can I do with electricity? Can anybody suggest? What kind of work can I do with electricity? Okay, so I can make heat, so I can do some thermal work, right? Thermal work, it means that I'm making things hotter. Sometimes it's on purpose. If I have an oven, sometimes it's not on purpose. If my phone or my PC gets hot. What other kinds of work can I do? Okay, so where's mechanical work? Very good. Mechanical work, moving stuff in space. Mechanical work. What example of mechanical work is very common? And that is playing sound. When you play sound, you have a diaphragm in your speaker, and you move it using electricity. And this is how you make sound. What other kinds of work can you do? Any other ideas? Computation work. Okay, that's very important for us in this course. Indeed, Elena, we need to make computations, and computations means I'll talk about how do you do computation using electricity in good detail later today. But indeed, I want to do computation with electricity. What is the last thing that we can kind of think of? Radio. Okay, radio is electromagnetic work, indeed. So just like in radiate heat, I can radiate other kinds of. I can radiate electricity and so on. What else? So the last thing I want to talk about is chemical work. What is chemical work? Charging the battery. Yes, electrolysis or just charging a battery. So a battery has a charge carrier. It has a certain solution of ions in the solution. And when I'm charging the battery, I'm actually moving. I'm doing some chemical transformations on the battery and getting it ready to serve power. So I can do all sorts of things with my power. And I think the most important thing or interesting thing for me as an attacker is doing computational work using electronics and then measuring. So one thing which is kind of subtle and I want to cover is when is power consumed. So this is a kind of a nice circuit. It has the power coming in here and getting out there. This is nice, but sometimes you have devices where the power comes in and it doesn't come out. For example, when I'm charging my phone, the power stays inside the phone. So when am I consuming it? Or when I'm running off battery power, the power isn't coming in. So I'm going to, maybe artificially, but I'm going to define that I'm consuming power when it travels into the ground, when it goes into the ground terminal or the actual ground of the battery. So if it gets stuck in here, I'm not consuming it.